Okay, so let's talk a little bit more about limits. You're going to hear a lot of language and stuff that sounds very strange here, so I don't want you to get too hung up in the formal definition, but I want to go ahead and give the formal definition so you have it. Limits give us a language for describing how the outputs of a function behave as the input approaches a particular value. We have to keep that in mind, the approaches, because that becomes very important in the concept of limits. In the example previous, in the instantaneous speed example, we didn't evaluate what happened at precisely h equals 0 or when what happened exactly at 2, but rather we examined what happened as h got closer to 0. And remember, if you h was just a very small increment off that time. So in the concept of limits, we don't need to know what's going on at precisely a moment in time. We don't need to know what happened at exactly 2, or what happened when our time increment was 0, so we don't have that divide by 0. We can look at what's happening on either side of that value as it's getting closer and closer and closer to it. And that's what all this formalized definition of a limit is. We were able to see this algebraically. And if you'll remember in the notes, I gave you the algebraic proof of what you did in the table example. But the algebraic version isn't always possible for us to do. Most of the times, but not all the time. So this gives us a formal definition of the limit. And again, please don't panic when you see this. The formal definition says, let C and L be real numbers. The function f has a limit L as x approaches C, and that's just some number. If given any positive number epsilon, there's a positive number delta such that for all x, 0 is less than the absolute value of x minus c is less than delta. Therefore, the absolute value of f of x minus L is less than epsilon. Don't panic on that. I'm going to show you a little graphic of that, and you'll kind of see what I'm talking about. I just want to feel for it. I don't want you to have to worry about those exact words and the epsilons and the deltas. Don't get hung up in it. What I do want you to remember, though, is right here. We write and say the limit of f of x. I'm sorry, let me repeat that. The limit as x approaches c, the limit as x approaches c of f of x equals L. Get used to saying that. You'll say it a lot. The limit as x approaches some number of some function equals some number. We'll talk about how to formalize and find these. But if we look at this graphic here, all of that formal definition is saying is, I have some number c on the x-axis, and maybe this line here is my function. So somewhere on the c, on this graph, is a value x, like c, and somewhere it has an output L. Somewhere in between, a little bit less, so c minus delta, or a little bit more, c plus delta, there's an output, the limit plus epsilon or the limit minus epsilon. And somewhere very close to these values is a limit, or a value as it approaches. The interval, and this always sounds very strange, but it will come clear, I promise. The interval on the x-axis contains c, except possibly exactly at c. And again, I'll show you more versions where this actually happens. So basically it just says that the limit will be found really close to c, but not necessarily at c. And this idea of approach becomes more important later. So just kind of keep this in mind as the definition of a limit. Next up, I'm going to show you some formalized algebraic ways of finding limits. Might make a little bit more sense to you. Actually, the first few will probably seem really easy. So just remember, when we're talking about limits, we're not talking about values at a specific value. We are talking about values as it approaches that value.